Well, it's 11:20, and I guess we can go ahead and get started. I hope everybody's well, and I hope everybody's staying safe. My name is Mabby Amouie. I'm the director and chief data scientist at Norfolk Southern. I oversee everything AI, data science, and data engineering related at Norfolk Southern. And we thought that this is a good opportunity to give you guys a little bit of perspective about actually who we are and what we do. And then why do we even, as a railroad, need ML and DL? What's the whole point of it? I guess railroads are traditional industry, right? You just haul cars and trains. So I want to touch a little bit on there. And then I want to showcase one of our use cases, the automated asset inventory using deep learning, and give you some challenges and tips for putting the model in production. And it was a challenging model. It has its own quirks, and I want to talk about it a little bit and give you some tips that you might already know, but it was new to us to put TensorFlow on steroids. So, we are a railroad company. You can see the map here. We operate on the whole east of United States. 19,500 route miles of track, over 28,000 miles of track that we own and operate. We serve over 6,400 customers, had a revenue of $11.5 billion. And we really ship from anything from raw material, automotive, cars, anything you can even think about. So a big part of our business is intermodal. Those containers that you see on the trucks, those containers that go on the ship, and basically anything from UPS packages, chemicals and oil, even DoD stuff, and all the way to finished products, appliances, and everything. So we pretty much ship everything. Now, you would, again, still wonder, why do you need data science, right? So we run thousands of trains daily. It's a network, so any disruption on anywhere in the network can have a ripple effect that can basically touch different parts of the network. So it's very important for us to have very highly reliable assets. And on the other side of the things, we are very asset intensive. And I'm going to talk about this. Our assets are very expensive. And you really want to make sure that you have full utilization on them and full reliability. We also have critical workforce, so productivity is very important for us. Now, as we talk about our assets, we have about 4,000 locomotives. Each locomotive is nearly $3 million a piece. And you can imagine it's very expensive. You don't want to have engine failures. You don't want to have things or maintenance that is very costly given the cost of the locomotives. And guess what? They are like Teslas of the world. They stream 350 sensors in real time to the back office and give us all the diagnostics that we need that later on we can create a predictive model on it. We also have track geometry cars. These are the rail cars that run over our tracks. And I'm going to talk about this a little bit more. And essentially, they have sensors and they measure everything about our tracks. They also have cameras and they can scan our tracks. All the way to the drones, and we also have high frame camera portals. So as the trains are passing by, the portals are capturing images of all the trains, and we later on create deep learning models that look at these images and say, do I see a defect or not? All the way at the edge, everything happens at the edge. So and everything automatically creates a work order. So pretty cool stuff. And here's our infrastructure, just for people who are a little curious about how we do these things. All kinds of databases on the left side, all kinds of IoT and cameras, but predominantly our data engineering team uses a Spark and Scoop and Kafka to bring the data. We have a Hadoop-based data lake, and on the right side is where our data scientists are focused, really are on Python, Jupyter, all kinds of good stuff, TensorFlow, Keras, PyTorch, and as you see, we don't really use anything proprietary. Everything is open source, and everything is the latest version of open source. We don't really lend ourselves to anything that kind of limits us from the functionality perspective or from how bleeding edge or cutting edge we want to be. Now, these are some of our use cases. The first one is the one that I'm going to talk to you about today and give you some tips on how you can optimize your deep learning models. It's around the automated asset inventory from the inspection images. We get about 500,000 images per day, which is a lot for at least our industry. And really, how are you going to have a deep learning model that can go through it with what infrastructure, and how do you do that in scale? We also predict locomotive component failures in advance of time. We have a few use cases in production since 2017 where we predict certain we call it mission critical, which is very critical components that if they fail, we're basically stranded on the line of road. And we predict those days in advance. So it gives us capability to basically plan better and route those locomotives in the shop. You can think about this with highway. If your car breaks down, you have so many lanes on the highway that you can pass by. With locomotives and trains, a lot of parts of our network is a single line of track. So if the locomotive breaks down, if your train is stranded there, you're going to block everybody behind you and everybody in front of you. So it's a mess, and it can propagate, as I said, because it's a network of trains. It can propagate all the way and have ripple effects and snowball. And the last thing is we detect defects from real-time images of our cars, the camera portals that I was talking to you all about. And everything happens at the edge. Cars are passing, images are captured in real time using high frame cameras. And we have these deep learning models that look at these images, find the defects for us, defects of interest or components of interest, and then basically send a notification back to say, hey, you know what, this car on this train, it needs immediate attention for this component or such component, or at the next stop, or, depending on the criticality of it. But let me talk to you all about the asset inventory, because that's one of the interesting use cases that we solved. And again, I wish I had time to go through all the different kinds of use cases that we work on. This is just the 3 snapshot of the use cases that we do in real life using machine learning and deep learning. So really the use case is detecting objects and assets on the rail. And I'll tell you why it's important and why in general. You can see on the left, there's a picture of a rail. You can see some surface damages, and you can see these boxes. And of course, it tells you that there was some either traditional computer vision algorithm or some deep learning model that looked at this and made that assessment, or maybe somebody just sat behind the PowerPoint and created those boxes. You'll never know. So rail assets really change on a daily basis. And it's very important to stay up to date with that, because you can think about, we have 28,000 miles of track that we operate, and it's impossible for someone to, or an army of people to walk along the tracks and always keep up with these changes, especially surface conditions, especially things like welds. You can imagine we find issues on our rails, we cut the rail and we put a new rail. And how do you do that? Well, you got to weld it to the existing rail. So again, all of a sudden welds start popping up, or a car was going for whatever reason, it caused surface damage. So these things change really every day. And it's very imperative for us to have accurate and up-to-date inventory. And as I said, it's not something humanly possible to just walk along the tracks all day, all long to try to find these things. And again, as I said, we have lots of miles of tracks, and it's simply impossible without some sort of automation. Now, what we do have is these rail cars called track geometry cars. They're just like any other rail cars that we haul. And these are equipped with sensors that essentially they read geometric information about the rails. And you see on the right side, in the bottom right corner, that you see all these measurements about the rail. And this is really the sole purpose of these track geometry cars. As they're running on the tracks, they capture these geometric information, and this geometric information change over time. And again, we have another predictive model that looks at that. But one of the things that we could leverage these cars for, well, these cars are going everywhere on our network on a daily basis to capture this information for us. So what if we have a downward facing camera on them, just like the one that you see on the top? Well, we have a camera that is taking pictures, and many of them. So can we utilize these camera images, have our deep learning model that would do the same thing for us as if someone would walk along our tracks for 28,000 miles and basically pinpoint every GPS location, every track, every issues on the left rail or right rail, and whatsoever. So as I said, these cars inspect about 50,000 miles of track every year. And you can imagine we only have 28,000 miles. So 50,000, in some cases, we measure them twice a year, 4 times a year, depending on how important those segments are. And I think this is where it gets interesting from the data science perspective, that you generate several millions of images on a weekly basis. And even if you have the best of the best deep learning model that you created, or a computer vision model that created, how are you going to put that in production and scale up to scoring several millions of images on a weekly basis, and also do an inventory on them, right? Because things change. So you kind of need to have that change detection. I'm going to talk to you a little bit more about it. Just to give you some flavor of how these images look, again, on the left side, you see some surface issues. On the right side, you see those kind of tiny lines those are indication of welds. If you were to look at this rail from the right side, you would be able to see actually how things align, that they welded. But on the top side, you can see from the top that there is a weld there. And you can see that the algorithm is correctly identifying that. Now, the question becomes, again, 28,000 miles, continuous imaging, and millions of images in each pass. What kind of architecture do you create? And what kind of tips and practices did you put in place to be able to scale this and actually be able to run it? Because on paper, it seems like you need a GPU farm to be able to process this. Here's how the architecture looks like. And I'm going to just break this down. It's a very simple architecture. It doesn't have anything too fancy about it. You see on the left side, we are collecting the images. And then you have this GPU cluster that you do parallel training, and later on you utilize it for parallel inference as you're getting these images. You can see that I have the TensorFlow Keras and OpenCV logos up there. I did not put PyTorch because this very use case that we solved, we did not use PyTorch for it. And then, so basically the flow is that you collect these images, you run your inference. It tells you for every image, basically, whether you see a weld, whether you see a surface condition or whatnot. Well, then later on, that's all you did for that image. You need to pass it and do an inventory, right? And for that, we're talking about tons of data points. You can imagine as these rail cars are moving on our tracks, every foot they're capturing a data point. And 28,000 miles, 28,000 times 5,200, 5,280, it's going to be a big number, right? And we have multiple of these cars. So we leverage Spark basically to update that inventory. And you can see that we also have a Parquet file. So we run this inventory once, we baseline it, and we save it in the Parquet format. Later on, as we do additional inference, we go back, read that Parquet format, run the Spark algorithm on it, update the inventory. And this is really going to feed into a couple of things. One is a GIS system that we have internally where we have all of our assets mapped out. And we also feed it into a dashboard for other users, a Tableau dashboard. Now you can see there's an arrow that goes back to the parallel inference and training, because we gave the users this capability that for every image that they get, if they see anything was a false positive, something that the model thought it was a weld or it was a surface condition, but indeed it wasn't. Maybe it was a leaf on the rail, or there was just something that resembled itself and confused the deep learning model. So the users can have that feedback. Basically, it can count it as false positive. It goes back to the basically the training pool, so that next time we train the model, we incorporate these false positive and basically help the model learn from those mistakes that it made. So on the surface, it's a very simple architecture. Then why are the challenges, and why we keep talking about the challenges? This is how it looks like on just a simple Tableau dashboard. You can see all these different points. Each point is an asset that we are detecting from these images. And if I just zoom in, this is what you get. You see lots of different points. I'm not sure if I can show you with my mouse. Lots of different points here with different colors. Each color is representing an asset that we are finding on the rail. And you can see, it might be very small, but there are 2 tracks. So specifically where you're putting these assets, these are all getting detected properly. And if I just hover over any point, it can tell you the type it is. It says, oh, well, I have a weld. It's on track 2. Here's a distance matched to the center line of track. This is the last inspection date that you had for it. This is its lat long trimmed version, and this is the object that I'm not going to get into. But the cool capability about it is that you can click and this image pops up. So you can immediately see if your model did the right job. And imagine that that asset was something that you wanted to go and visually inspect. Well, now you can literally instruct someone that, hey, here's the image, here's where it's located. Just go there and try to see, try to inspect it, or try to further look at it, or do whatever you want to do with it. And again, as I said, this continuously gets updated. So it's pretty cool. Like next time that, let's say, track geometry car ran on this and you didn't have that asset anymore, let's say you replace this rail, well, this is not going to get detected. The inventory gets updated. So every time you go to the dashboard, you have the latest information based on when you last inspected it. Something that, again, wasn't possible. It's by no means possible for someone to walk along the tracks and do this. And the other thing is that the accuracy is going to be very different for people to do it with their GPS devices versus for this highly accurate rail car that is running. And again, it all goes back to how accurate your deep learning model is, which ours was very accurate in this case. Now, I want to close this by giving you the challenges that we had, the tips that we used to overcome those challenges. I know a lot of people might be data scientists here, and the challenges that you face in production is very different from the challenges that you face in a non-production environment. And here in this case, again, millions of images. So just to give you another backdrop, again, this was our architecture. The challenges are you get a lot of images, you have limits to the infrastructure that you have, and of course the amount of the speed that you have to basically run your inference, run your post-process and everything. And of course, a lot of historical data points for cross-referencing. So there's a lot of challenges there too. But I want to focus on the deep learning part of it because that's a hot topic this day. So again, putting TensorFlow on steroids here on spinach. But I'm going to talk to you about the training challenges. Well, we had unbalanced data set, not new to anybody. Everybody deals with it. But the difference here is that we had severely unbalanced data sets. Some of our assets, we had too many of them, some of them not that much. Of course, just like anybody does, we did various augmentations, but that did not give us enough boost. Upsampling, downsampling, not so much boost. What really gave us a boost was a custom mini batch generator that we created, and we kind of forced first sampling. So you can imagine with micro batching, you always make sure that your batches are randomly selected so that you do one pass on the data. Here, what we did, we said, for every mini batch, I don't care if I'm looking at different passes of data. Every time I'm going to sample X number of surface conditions, Y number of welds, and Z number of something else, and I'm kind of balancing it randomly every time that I'm mini batching. And you can imagine as n goes to infinity, you have already looked at the whole data set and you have looked at it multiple times. So that's what we did, and tell you what, this was a huge boost for us. But really, this wasn't the challenge. I mean, creating a deep learning model wasn't the challenge as much as how you really had to productionize it to scale it up. So the inference was the challenge, and the most important one was the speed. So the first thing that we did, we parallelized both training and inference. There are many ways to do it. Horovod was the cool things at the time that Uber created. Everybody uses Horovod. PyTorch now has parallel inference and parallel training, but we use TF2.x. And that API was good enough for us. But I'm also going to give you a little bit of tips, given that we only have 2 minutes left, or now 1 minute. We enabled AMP, automated mixed precision training. It gave us a huge boost because, with a lot of computation, TensorFlow uses a float 32. It's not needed necessarily. So when you enable AMP, it automatically tries to do some conversions so that you don't have to have float 32 everywhere. And it really helped us, with the speed. XLA was another one that, it's just one line of code that you use, but because of library that it uses, make it very fast. I would not stress enough on batch inference as opposed to one at a time. A lot of us get one image, call the model that predict on it, and that's it. But batch your images and batch it as large of a batch as you can. Make it 1,000 images, whatever fits in memory. Read the 1,000 images, pre-process them, give the 1,000 one at a time. Not one at a time, sorry. Give the 1,000 in one batch to the model, predict it, and again segregate it to one at a time. And again, pick the largest batch size you can, pick the smallest input you can, because just because your input is 512 by 512 doesn't mean that you need that. And two other things, pick the backbone that makes sense. A lot of our backbones are very complex, and you really don't need that, because some of our use cases are much simpler than use cases like ImageNet or Cocoa and things like that. And one last point, now that we're at finish line, quantize. Quantize your model. I cannot stress enough on quantization. Of course, look to see if you have any accuracy drops, but quantize as much as possible. And again, the combination of these factors really help us, score this in real time as fast as possible that we could get to be able to scale it to 50 million images. I know there are some questions. I'm gonna create a new breakout room just for the QA, and happy to answer any questions that you guys have. So I want to thank you all for listening. Thanks, guys. Stay safe.